Okay, let's dive right into this one. We've got a really cool mathematical puzzle on our hands today. It's kind of like a classic mystery novel, you know? We're trying to solve for something, but it feels like we're missing all the key pieces of information. It's a real matrix mystery. I mean, seriously, think about it for a second. How on earth are you supposed to solve a problem when the numbers that literally define the problem are just unknown variables? It sounds completely impossible, right? Well, as we're about to find out, sometimes the most abstract clues are way more powerful than a bunch of concrete numbers. All right, so here's our main suspect. This matrix right here, this is our linear transformation, t, squared. And as you can plainly see, it's just full of unknowns. We've got an a and a b floating around in there. We have no clue what they are. So where do we even start? How can we possibly analyze this thing, let alone find something like its kernel? Well, this is where the real detective work kicks in, because even though we don't know A and B, we have been given two absolutely critical clues about the original transformation, T. And trust me, these two little clues are the key to cracking this whole case wide open. Now, at first glance, these clues look super abstract, maybe even a little intimidating. First, we're told the kernel of T isn't trivial. All that means is that something other than the zero vector gets mapped to zero. And second, and this is the really weird one, the kernel is a subset of the image. So let's do a quick refresh on what these terms mean. The kernel, you can think of it as the set of all the inputs that our transformation just completely flattens or squashes all the way down to zero. It's kind of like the vanishing point of linear algebra. The image is pretty much the exact opposite. It's the entire set of all possible outputs. So if you take every single vector you can think of and throw it at the transformation, the collection of all the places they land, well, that's the image. It's the transformation's entire playing field. Okay, so let's go back to that bizarre second clue. The kernel is inside the image. What does that actually mean? It means that any vector that our transformation squashes to zero must also be a possible output from the transformation. It's a vector that plays this strange double role. It's in the landing zone, but it's also an input that gets sent to oblivion. And that right there is a really specific, really powerful constraint. Now, when you put those two abstract clues together, something amazing happens. They lead us to this incredible logical breakthrough. This is the big aha moment, the insight that's going to let us completely sidestep the fact we don't know A or B and just cut straight to the answer. Let's walk through this together step by step. So we know there's some non-zero vector, let's call it V, that's in both the kernel and the image. Okay, because V is in the image, that means there has to be some other vector, we'll call it U, where T of U equals V. Simple enough. Now, what happens if we apply the transformation twice to U? Well, T squared of U is just T of U, which is T of V. But wait, we already know V is in the kernel, so T of V has to be 0. This means U gets sent to 0 by T squared. But, and here's the real kicker, U itself does not get sent to 0 by T, because T of U is V, which we know isn't 0. And boom, that's the core discovery. We just proved, right here, that there's at least one vector, our vector U, that's in the kernel of T squared, but is not in the kernel of T. This means the kernel of T squared is actually provably bigger than the kernel of T. This changes everything. And of course, if one space is strictly bigger than another, its dimension has to be bigger too. So the absolute crucial takeaway is this. The dimension of the kernel of T must be strictly less than the dimension of the kernel of T squared. This one little inequality, this is the weapon we're going to use to solve the whole puzzle. Okay, so now we're armed with this incredibly powerful piece of abstract knowledge. Let's head back to that messy matrix full of unknowns and finally solve this thing once and for all. All right, let's just lay out the logic here. We're working in a 3D space. Because the kernel is a non-zero subspace of the image, we know its dimension has to be smaller. The rank nullity theorem tells us these two dimensions have to add up to 3. Well, the only way that works is if the kernel's dimension is 1 and the image's dimension is 2. Okay, now we bring in our key insight. The dimension of the kernel of T squared has to be greater than 1. And since our matrix obviously isn't the zero matrix, its kernel can't be the entire 3D space, so its dimension has to be less than 3. So what's the only integer between 1 and 3? It's 2! The dimension of the kernel of T squared has to be 2. There's no other possibility. So, if the dimension of the kernel of T squared is 2, what does that tell us about its image? Remember, Kernel dimension plus image dimension equals the total dimension of the space. So 2 plus what equals 3? That's right. The dimension of the image of t squared must be 1. And here, my friends, is where it all clicks into place. A transformation whose image has dimension 1 is represented by a matrix with a rank of 1. And a rank 1 matrix has this one beautiful, simple property. All of its rows are just multiples of each other. They're all proportional. Suddenly, we don't care what A and B are anymore. We just know the rows have to be related in this very specific way. So we just set the second row to be some multiple, let's call it T, of the first row. That gives us this simple little system of equations. Now look at that third equation. It tells us that either T is 0 or B must equal 2A. A quick check shows that T equals 0 doesn't work. It leads to a contradiction. So we know B has to be 2A. We plug that back into the other equations and we get one and only one unique solution. A has to be 4 and B has to be 8. And just like that, the mystery is solved. And there it is. Look at that. The unknowns are totally gone. We plug in A equals 4 and B equals 8, and we get our final beautiful matrix. And notice, the second row is exactly negative 1/2 of the first, and the third row is all zeros. It perfectly satisfies that rank 1 condition we discovered. It all fits. From this point on, it's pretty much smooth sailing. We can just row reduce our solved matrix, find the basis for the kernel in coordinate form, and then translate those coordinates back into the polynomial basis from the original problem. And with that, we have our answer. A really elegant end to a tricky puzzle. So I think the big takeaway here is just how incredibly powerful abstract reasoning can be. We started with this concrete problem we couldn't possibly solve head-on. Then we used these abstract properties to deduce a hidden fact about its structure. And then we used that fact to find the actual concrete numbers. It really makes you wonder, right? What other hidden structures are out there, just waiting for us to find them with a little bit of pure theory?